Okay, now it's my pleasure to introduce our keynote speaker, Professor Ahmed Busnaina. Ahmed is the William Lincoln Smith Chair Professor. He's a distinguished university professor and founding director of the NSF Nanoscale Science and Engineering Center for High-Rate Nanomanufacturing and the NSF Center for Nano and Microcontamination Control at Northeastern University in Boston. His research support has exceeded $50 million. He's authored more than 600 papers in journals, proceedings, and conferences, in addition to 25 patents. He's an associate editor of the Journal of Nanoparticle Research. He serves on many boards. He's a fellow of the American Society of Mechanical Engineers and the Adhesion Society. He was a Fulbright Senior Scholar and listed in Who's Who in the World. So he's going to talk to us today about trillions of sensors for healthcare. Professor Busnaina.
Thank you very much. And thank you. I'd like to thank iMAPS president and organizers for inviting me. It's very. I'm very happy to be here. So I'm going to talk about sensors, but they're not the typical sensors that you know. They're not conventionally made sensors. For example, like semiconductor fabrication based sensors, although the theory may be the same, but the manufacturing process is completely different. So I will start with an introduction about this new technology. And then the motivation for that, there's a few motivations. And then talk about the state-of-the-art printing of electronics right now. And then talk about the technology, which is we call directed assembly-based printing technology. And then talk about other types of making electronics and sensors by interconnecting layers, which many of you know, because when you look at printed circuit board, it's all interconnected. You have multi-layers interconnected, but the way printed electronics is done today, it is not interconnected. It's just printing on the same surface. And then I'm going to talk about the printing system that we built, and then get into sensor applications, chemical sensors, biosensors for pathogens and for different biomarkers, for example, diseases, pathogens, as well as physiological monitoring. So the first thing that was really the real motivation from the very, very beginning was, what if designers had complete freedom to use whatever material they wanted on any substrate they wanted, without the process affecting whatever they manufacture? And that was our goal from the very beginning. What if you start with a polymer? You can put silicon on top of that. You can put carbon nanotubes. You can put quantum dots. You can put interconnects of any material you want, including carbon nanotubes, for example. What if you use different semiconductors? Silicon, 3,5, graphene, although graphene is not really a semiconductor, molybdenum disulfide, and other 2D material semiconducting properties. What if that is possible? That was our motivation. And we were funded by the National Science Foundation to develop such technology. And that means starting with nanomaterials, how can you build devices such as these? And so basically, this is the future of manufacturing. It's a directed assembly-based printing. How does it work? You build things bottom up, just like nature. Everything nature is done cell by cell, molecule by molecule. We do the same thing here, molecule by molecule, particle by particle, using self-directed assembly, just like nature, except we don't want to be as slow as nature. Look at a tree, it takes many, many years to build a tree. We don't want to do that. We want to be very fast. Also, we want to be faster than conventional fabrication. And also, we want to build devices at room temperature, ambient temperature, and pressure. We don't want to use vacuum. We don't want to use high temperature. And we want to build it on either flexible substrates or rigid substrates. And on top of that, the manufacturing process or the printing process has to be extremely cheap, has to be a fraction of the cost that you would incur if you built the exact same device, for example, using semiconductor fabrication. So the first motivation is basically the IoT. I'm sure you heard so much about it, the Internet of Things. And the interesting thing about this Internet of Things is that you have what they call it the five verticals. You know, the wearables, the cars, the homes, which is already happening, and then you have the cities and industrial internet, which is the biggest commercial application. And the first thing that you see when you look at this, you say, well, you know, this is not possible unless I have trillions of sensors embedded everywhere. And that will not use as much power as well. And to do that, you have to have ubiquitous sensors that are very inexpensive and also use less power. I just have an example here about the Fitbit, for example. I think some of you probably have Fitbits. The Fitbit, when they went for their IPO in June of last year, they were expecting to raise $600 million. They raised $6 billion. Question is why? They have no new technology. Everything they had in the Fitbit was already existed before. All they had was just software to collect information and transmit that to your phone. The reason for that is because of the IoT promise, because they expect that this is the first company that is using wearables and getting to be the first in the market. And that's why it raised $6.5 billion, not $600 million. Another slide about also the IoT total value for the next 10 years. The total value is about $2.3 trillion, but that includes software. The hardware value for the next 10 years for the IoT is about $500 billion. So that's also very, very large. The wearables market, which is still small, very small right now, although it's growing by leaps and bounds every year. The current one is about 24 billion. And in 10 years, it's supposed to increase to 64 billion. And I think that with new technology, probably will exceed that. The other thing that also was a motivation for us is to have sensors that are easier to use. For example, let's take glucose. Okay, so everybody that monitor glucose on their own, you have to use blood, right? So you have to use a lancer, get the blood, then get the droplets, and use these strips. And each strip is used only once, and you throw it away. We wanted to use sensors that are easier to use, cheaper, portable, can be integrated with your phone, for example, but also does not use blood. Uses something like tears, sweat, or saliva, for example. And that's possible. And so that was the motivation. So to make these sensors affordable and ubiquitous and cost-effective, the fabrication right now is getting, especially at the nanoscale, is getting more expensive. And so one of the ways to reduce the cost is to use printing. And so let's look at the printing right now, today. The printing today is, we already see printed things, such as the Kindle reader. We've seen that, the black and white Kindle. That's printed, for example. Your RFID tags are printed. Most of the printed electronics use organic electronics, not inorganic electronics. And the RFID tags basically that are printed, they're not really printed. They only print the antenna. If you look at the RFID tag and just touch it, you will find a small silicon chip that's glued on the antenna. So even the RFID tags are not printed. Only the antenna is printed. Why we can't use that now? Well, there are some problems with the technology, the way the technology works today. The first one is scale. The smallest line width that you can print today using the best commercial technology available is about 20 micron. 20 micron was the line width in 1975 for silicon chips. So it's more than 40-year-old scale. The other thing is that they don't do interconnected multi-layers. such as CMOS, for example, or even printed circuit boards. They just print on the same surface. And also they have some limitations in some of the material they can use, because you have to prepare some ink, you have to use a lot of chemistry, and some of these inks are very, very expensive. So, does that mean it's not good? No. It's actually still has a huge cost advantage, between 1/10 to 1/100th of the cost of a similar printed sensor, for example. If you take a sensor made using a conventional semiconductor fabrication, for example, and a printed sensor, the cost is between 1/10 to 1/100th of a similarly based sensor, conventionally made. And the difference is that the 1/10 is a simple sensor, the 1/100th is a more sophisticated system. The printed electronics right now is about $40 billion a year, and it's growing. But the printed sensor is still a very, very small market. It's about 300 million. So what we wanted to do is we wanted to leap with printing from 1975 to today. Leap 40 years, at least in scale. And that means first that we have to do accomplish printing at the nanoscale, which means that we have to print, have the smallest line width, for example, to be 20 nanometers instead of 20 micron, 1,000 times smaller. But the question is that enough? Well, in most cases, it's not enough. It's enough to publish a paper, maybe, or to talk about it, but it's not enough to make a product. What makes it, so what do we need in addition to printing at the nanoscale? We need two more things. We need to have a system that's orders of magnitude faster than inkjet, to be 100 to 1,000 times faster. Because if you're doing inkjet, it's going to take forever to print any nanocircuit. Also, the cost has to be still a fraction of the cost of doing it in silicon. If it's the same, there's no value added. So I'm going to show you the tool that we built to do that. And actually, it's in Burlington, Mass. And so let me show you how does it work. It's actually very simple. We make templates. We use templates. They're just like the old printing plates for books and so forth. But this template is made using semiconductor fabrication. And this template uses electrophoresis. So we put the template in. You have embedded wires in the template. You apply about 2 volts between the counter electrode and the template. This is the template. And then basically all the ink particles will land on exactly the pattern, even if your pattern is 20 nanometers or even smaller. Once you ink the template using directed assembly, you print and you transfer the whole pattern into another substrate. This works for flexible substrate, flexible electronics. But we have other techniques that will print it on any surface: ceramic, glass, silicon, whatever surface you want. Because remember, this is based on physical chemistry only. There's no etching, there's no CVD, there's no vacuum. So it's very, very easy to print different materials. So the thing is that, is it good just for electronics? No, we actually done so many different applications with that. So electronics is one of them. We've done metamaterials, we've done radar, we've done shielding, we have done batteries, although you don't really need patterning for batteries. We've done energy harvesting. We have done different types of electronics, flexible and non-flexible. We've done NEMS, nano electromechanical systems. We've done biosensors, which I'm going to talk about today. We also have used the technique to print drugs, to make insoluble drugs soluble. There's a lot of drugs that have to be injected. They cannot be taken as a pill. So we found out that if we take the drug and actually print it in a specific geometry, very small nanoscale, it can be taken as in a pill, and you don't need to take injections anymore, or intravenous administration of drugs. Okay, so let me show this slide, which just summarizes what I just showed you, the animation that I showed you. So we have the template. We functionalize the template so that you'll have hydrophobic or hydrophilic. So the conductor will be hydrophilic, water-friendly, so that when you apply the voltage, the particles or ink particles or the nanotubes or whatever you want to print will be attracted to that surface. The rest of the surface is hydrophobic, so you don't want anything to land there. And then once you do that, you put it in the solution, suspension, most of our suspensions are water. 95% of our suspensions are water. But if you need to use DMF, NMP, any solvent, you could use that. That's not a limitation. And then once you do the assembly, which takes a couple of minutes, you do the printing. And then once the printing is done, you will use the template. The template can be used thousands of times, same template. So you only need one template. And for each layer of the circuit, or the sensor, you have one template. Sort of like a mask. For each layer, you have a mask. But remember, this is all additive. There is no removal of material. So it is high throughput because you print the whole macro, micro, and nano structure in one shot, one step. And we've done it down to 20 nanometers. It can be done smaller, depending on what lithography used, for example. It is ambient temperature and pressure. Can print it on rigid or flexible surfaces. It is material independent. We've done organic, inorganic. We've done conductors, semiconductors, and insulating material. And it's very low energy consumption and very low capital investment. I'll show you what the system looks like. You can do 2 dimensions, and you can do 3 dimensions. You can do things that you cannot. It's very hard to use without printing. For example, like carbon nanotubes or graphene. To print large structures with that, printing is really the best way to do it. The other ways are very, very difficult. And so there are a lot of examples that we've done here. For example, this is 3-dimensional. This is carbon nanotube, and so forth. Let me show you what the template looks like. So this is what the template looks like. Most of the stuff you see here is micro scale, but there are nanoscale as well. And so what we have done is we made the template such that wherever you assemble, wherever you have a pattern, it doesn't matter if your pattern is 20 nanometer or 20 micron or 200 micron. The ink or the assembly thickness, material thickness will be the same anywhere. Okay? So it's very well controlled. And we do that by making sure that the voltage is the same at any pattern, no matter how small it is. And this one is made on silicon, so you have the backing is silicon, and then you have tungsten. We have used tungsten, we have used gold, we have used, but the best material to use is actually nickel for these kind of templates. But you can also, instead of using silicon as the backing material, you can also use polymer. So we did PN, we've done polyimide, for example, and for this one, if you want to use this on a roll-to-roll system, for example, you could. This is one example where when we print the carbon nanotubes, actually they're aligned, which is very useful if you're doing sensors, for example, because you get a very much better and much more consistent resistance, for example, in your channel. This is printed polystyrene latex particles that are red fluorescent. This is silica particles that are green fluorescent. And so this is just printing one layer. But when you're printing multi-layers with a dielectric in between, you need to actually have the interconnect. So how do you do the interconnect? So we developed a way to do the interconnect, and just using also directed assembly. So you have the via, and you provide low voltage, but less than 2 volts at the bottom of the via, and then the particles will assemble, and they will fuse at room temperature. And we've done this with copper, gold, silver, indium, aluminum. We've done about at least 7 conductors. And we tested gold, for example, and the resistance for a 15 nanometer interconnect has an aspect ratio of 3 to 4 was the same as electroplated gold. For tungsten, same dimension, was exactly the same as tungsten CVD. So the values were the same. So what we did is we showed this technology about 3 years ago to companies, and we get companies from Intel and from these, and they come in and say, "Oh, this is really nice." And we show it in a beaker and a lab bench and so forth. And they say, "Well, what is your yield?" And I say, "Well, depends on the students who's doing it." And they say, "What do you mean?" And I say, "Well, some students get 90% yield, some students get 10% yield, And they say, "Well, what do you mean it's not repeatable?" And I say, "No, it is repeatable. It's just students usually skip a lot of steps So we said, well, and they said, is it scalable? And we said, yeah, it's scalable. We've done 4-inch, we've done 8-inch. They said, well, but we see you work with really small chips. You know, we don't see the scalability. So we said, okay, we have to put a system to print, and that takes the student as well as the operator out of the process. We wanted to build a fully automated printing system that does exactly what I was just talking about, but does it fully automated so that you put the recipe in the computer and just let it go and no one touches anything. And that's what we built. You know, we built it, we're using a cluster tool. A lot of you probably are familiar with the cluster tools. I'm familiar with the cluster tools. I worked with the semiconductor industry for 25 years. I worked on copper interconnects, I worked on tungsten CVD, tinitride PVD, I worked with tools, I worked with applied. I have my students in IBM, Applied Materials. One of my students is a corporate vice president for Applied Materials. So I know the industry very well. So we decided to use a cluster tool, mainly because we have few steps, just like cluster tool, for example. And so, and this one, for example, the templates go here, the substrate go here. This is the inking or directed assembly. This is the transfer. And we have a built-in registration and alignment module, because you have to align. And so with this one, it allowed us to do 1,000 times faster and 1,000 times smaller structures. If you want to take a look at it, I will not show the whole video, but there is a video on YouTube. And you can, if you look for Nano OPS, Nano Offset Printing System, there will be 2 videos. One, like this one, made by my students, and one was made by the National Science Foundation that does explain the technology. And one, there's one documentary made by the Museum of Science, Boston. It's called From Lab to Fab. And that's a 22-minute documentary, very professionally done by Larry Klein, who's a producer who makes Nova movies. And he has a lot of movies on PBS. Just that, make sure that when you look on YouTube, when you say From Lab to Fab, it will say, do you mean from flab to fab? So you want to click on Lab to Fab. So this shows here, for example, that it picks up the template. So the template is picked up here, and then you do pre-alignment. Our template's like wafer, so when the robot picks it up, it doesn't know which end is up, because there is a contact at the top, so to apply the voltage. So you use a pre-alignment to find out where the notch is or where the flat side is, depending on the size of the wafer, and then it takes it to the assembly station. So here, the assembly station, you can see there are three tanks here. Each one has different ink. So one will have the silver ink, for example. One will have carbon nanotubes, and then the assembly takes place here. And then once it's done, you cover the other tanks first, because you don't want to drip from one tank into the other, and then you take it to an air knife station so that you dry it before you do the transfer. And then this is the air knife, for example. And once you do that, then you take it to the aligner. The substrate already is in the aligner. It was put there before. And then you take that in the aligner. Of course, we do put the fiducials. We print the fiducials. So when you have multiple layers, this aligner is actually micro. So it has an overlay of 2 micron. We're trying to go down to 15 nanometers, but we need a much more expensive aligner to do that. So basically, after you pick it up from the assembly station, you still have to pre-align it, and then you take it to the aligner now. And the aligner now, it's optical, so it looks at the box, it looks at the cross, and you put the cross in the box. And then once that's done, it gets pressed together, and then together they get taken to the transfer station, which is the printing station. And the printing station is very, very simple. What you have to do is you heat the plastic substrate, depending on which plastic or which polymer you have. And in this case, this is PETG. So you want to heat it up to maybe 80 degrees Celsius, which is a little bit below its TG temperature. You don't want to exceed the transition glass temperature of the polymer. Then the printing takes about 30 seconds. Then you cool it, and then you separate them. Puff of air will separate them, and then the template is at the bottom, so it goes to the bottom chuck, and the substrate goes upside down to the top chuck, and then you get collected. And so The cycle takes about 5 minutes, so in 5 minutes you're actually done, 5 to 6 minutes, you're actually done with one layer. That includes all the handling, that includes the alignment, that includes the printing, includes all that stuff, includes also the pre-alignment. Because each time you pick up a template or substrate, you have to pre-align. So anyway, so there are, if you have time, you can check that on YouTube. It's all there. And if you use this technology, you know, I mean, all of us probably heard about, I mean, when I was in the 1990s, when I was working with IBM, we had lots of projects with IBM. A cost of a fab in 1990 was 1 billion. Of course, now it's 15 billion. Okay, so and it's so expensive that now only 4 companies in the world can afford to build those fabs: Samsung, Intel, TSMC, and Global Foundries. Micron probably will not build any fabs anymore. You know, so basically, I think that with this technology, you can build a fab for under $100 million. And like I said, you know, if you actually want to visit, it's in the Costas building on the Burlington campus. Let us know, and we'll make sure that you can take a look at it. You know, see a demonstration. We just got the Printed Electronic Europe Award last week, and we got the R&D finalist. We got Wired magazine wrote about this and so forth. We work very closely with lots of companies, and so we have a good partnership with many companies. And the reason I show this slide is not to show you the name of the companies, actually, to show you how diverse these companies are. Because you have equipment companies, you have polymer companies, you have electronics companies, you have aerospace companies, you have electronic material company, you have chemical companies. It's a very, very diverse, which shows you the diversity of the technology, that it can be applied to a variety of applications. Okay, so I only have one slide about electronics. I'm giving another talk in the afternoon about electronics, more detailed electronics. I'm going to focus here about sensors. But this is just one slide about electronics that shows some of the electronics that we have done. We focused on doing new 2D material electronics, which is, you probably heard about graphene, of course. But graphene is actually losing favor now. People are using black phosphorus, using molybdenum disulfide, using other 2D materials that are much better because they are semiconductors, where the graphene is a semi-metal. It's not semiconductor. Okay, has a zero band gap. So we use graphene, printed graphene transistor. Graphene is molybdenum disulfide is N-type. So we made a transistor. We also made an inverter, because you can take carbon nanotubes, which are P-type, and then you have molybdenum disulfide N-type, and you can make an inverter out of those. So we did that. But we also have done a lot of carbon nanotube electronics. However, I probably should say this. I do not favor using carbon nanotubes for FET-based electronics. They can be used for other types of electronics, such as mechanical switches, for example. They work very well there. But they're not really good at using them as an FET. Why? Because so far you cannot buy fully semiconducting carbon nanotubes solution, for example. The best ones are about 99%, and they're full of surfactants, so they're really very difficult to handle. But a milligram is $1,000. So you can, I think a kilogram is like close to $1 million, for example, a kilogram. So it's actually very, very expensive. But that's not the only problem. Even 99% semiconducting is not as good, because that means you'll have transistors in the same circuit that have different on-off ratio. And so you have to deal with that. Now, if you use them for sensors, which what we do, that's not a problem, because each sensor has a base resistance, and you're actually measuring the change of that base resistance. And so that's okay. It's okay to have base resistance change from one sensor to another. That's not okay if you have a transistor in a circuit. Okay, so let's start with the sensors. So I'm going to talk about a few sensors that are chemical sensors, sensors for different biomarkers such as glucose, lactate, and so forth. And then I'm going to talk about sensors for pathogens. They all use the same pretty much architecture, very simple two-terminal device. So for example, let me start with the chemical sensor. This was done for the oil industry. And they wanted a few things done. They wanted to be very cheap. That's number one. Because what they wanted to throw tens of thousands under the reservoir and then reclaim them afterwards. And so they would lose about half of them at least. They wanted the sensor to detect things such as hydrogen sulfide, simple alkanes, thiol, and so forth. And they wanted to work at 200 degrees Celsius and high pressure. They also wanted to work, they were very specific, meaning that if you have other hydrocarbons, they should not be affected. If you have water, if you have water vapor, if you have them underwater, if you have nitrogen air, it doesn't matter. It shouldn't matter. So we did make that, and you can see the sensor is really small. It's about 1 micron by 10 micron, and actually it worked very well. This is the channel. Now, carbon nanotubes are sensitive to everything, but to have a good sensor, it has to be very specific, meaning it should only react or interact with what you want to detect, and that makes it specific. And so in this case, this was for hydrogen sulfide. So you have to make sure that the sensor will only respond to hydrogen sulfide and not anything else. So what you have to do is you have to find the molecule that will interact with hydrogen sulfide, either bind with it, and that way will affect the resistance. So here we tried 3 different molecules, all worked fine. This is the tempo molecule. You can also use 4-amino tempo molecule or tempol molecule. And so this is one sensor here. You can see this is an array of the sensors. And the sensor is chemoresistive. So when it interacts with hydrogen sulfide, the molecules change. And then that increases the resistance of the carbon nanotube. And so as a result, for example, at 10 ppm, you can see the current went down, which means the resistance increased. And the change was corresponding to the concentration. And the nice thing about this particular molecule, that's not the case with all molecules, of course, that it actually recovers, meaning that it goes back after it's exposed to air. So you use it, expose it to air, it's back. You can use it hundreds of times. It also works underwater. The only problem, it doesn't recover underwater. So you have to take it out in the air, recovers, put it back, for example. But you can get about 3 shots underwater. We also use it for hydrogen sulfide, like I said, nitrogen oxide, and a variety of other chemicals. It all depends on the molecules that you functionalize the channel with. Okay, so what about biosensors? Well, you can actually use the same, pretty much. The channel's dimension is different, as you will see, but you can use the same thing. So for example, this one has 100 sensors. Okay, this is a close-up of the sensors. These are all carbon nanotube sensors, and in this case, we functionalize these sensors, and it's very low power. For example, all you need is about 100 millivolt for the sensor, and the current is 1 milliamp. It's very, very low power, and so you functionalize it. And the functionalization actually is, if you're interested in that, you have a linker that links to the carbon nanotube, and then you put something like glucose oxidase or lactate oxidase. So when you have glucose, you put them in glucose oxidase, when it comes interact with each other, they produce electrons. So if the glucose oxidase is very close to the carbon nanotube, then the current will go up. But if it's too far, then actually the current will go down. So you can actually use it just like a CVS, glucose detector, for example, where the current will increase, and then the increase will correspond to the concentration of the glucose. So this is, for example, glucose, lactate, and urea, and you can see that the change every time you increase, or the current will go up. So you can actually do it either way. This project was started by funding from the Air Force. The Air Force wanted to look at how tired pilots are on long missions, for example. And so what they wanted a Band-Aid they can put on the pilot, for example. And the Band-Aid has a wicking mechanism, a capillary that will pull the sweat, for example, and then the sweat will pass by the channel and then will be wicked out, for example, and then you'll have a simple circuit with an RFID tag that will communicate with the airplane, for example. And then the Army also wanted it for soldiers, for example, to see how tired they are, because basically the lactate, urea, and glucose, especially glucose and lactate, will show how tired the person is, if he still have energy or not. And also it's good for training, of course, for athletes and so forth. This is the design that we have now. So we didn't want any other surfaces to interact with sweat, so we coated everything with the exception of a window on top of the carbon nanotubes. And you can see this is for lactate, for example. You can go down to about 0.5 millimolar, which is very, very low compared to the range for lactate is about 10, the normal range. So this is much, much lower. So you can go on the low side or you can go on the high side. You want to cover at least a good range. And also, these lactate and glucose sensors cannot be one-time use. The condition for the Air Force, they wanted to use for at least 3 days. Continuous use. No washing, no changing, and so forth. And so these sensors that we made actually would work at least for some that work 2 weeks, but they would all work for 1 week at least. Okay, so then we looked at other uses. So Professor April Gu, who's a colleague of mine at Northeastern in civil engineering, said, can I have some of these sensors unfunctionalized? I want to functionalize them myself. I said, yes. So I gave her lots of sensors, and she functionalized them using either DNA or using antibodies, for example. And she has been able to detect E. coli bacteria in water. This is drinking water. Viruses in water. It could be in drinking water. It could be in pools, swimming pool, or whatever it is, or rivers, for example. And also, she developed it to detect antibiotics. And I said, April, why antibiotics in the water? She says, well, there's a lot of antibiotics in the water we drink because, first of all, the body doesn't absorb the whole thing, so a lot of it goes, and lots of people actually flush things down the toilet, So it got to the point where water treatment systems, they want actually a threshold sensor to find out if the level, of these pharma products are high in the water. I remember 10 years ago I was in Scotland and I was talking to someone at the university there, and they told me that there was a one river in Scotland where the fish population all turned female. I'm saying, how could that happen? They said, because of estrogen in the water. I said, estrogen, where did it come from? He said, birth control pills. So these things are actually in the water, and we drink them and we don't know. So actually, it'd be good to actually have sensors like these, because if you don't have these sensors, you have to take a sample and take it to the lab and wait for a day or sometimes 2-3 days to find out. With these sensors, you put them in the water and they will transmit the signal, and you'll find out how the level changes. So these sensors are actually repeatable. So this is the E. coli bacteria sensor, for example, and you can see that it works very well. This is day 1 all the way to 23 days, for example. It works. It can only be used about 5 times, but it can last for about 3 weeks. We've done also, this is for the antibiotics detection, for example. It uses aptamers, and with the aptamers with DNA, for example, the OTC, that's the antibiotics. And then also, by the way, all these sensors can be used with blood. The only thing is with blood, they will not last for more than a couple of hours maybe, because blood has so many things in it that will biofoul and will coat the whole thing. This is also for the antibiotics, and this is the repeat, for example. You can see up to 30 days, and the response is still pretty good. For the viruses, you have to use antibodies. Now, antibodies, most people, if you've done any bio, they say antibodies, once you have the antigen, actually you cannot reuse it. You just throw it away. Actually, that's not the case. You can actually reuse it. And so April showed that you can reuse that. This is the detection. This is the binding time, because the antibodies have to have time to bind. You have antigens. So this is, for example, the antigen for the virus, and has to bind with the antibody. So you need some time to do that. And so here she shows 5 minutes is more than enough to do that. And then she shows the repeatability, for example. So here, first day, second day, up to 8th day, still the signal is pretty good, and the response, the sensor is very good. One more thing about the regeneration for the antibody. So this is how do you reuse the sensor with the antibody. So she showed that sodium hydroxide actually is very good, because you can go up to 10 days, still about 80% response. Okay, so my last slide basically shows how does this compare to existing sensors. Is it better? Is it the same? Is it cheaper? I have one example here, which is the commercial hydrogen sulfide sensor. It's about between 4 to 5 pounds, and it's about $400, one sensor. Okay, and by comparison, our sensor is very, very small. It's less than 0.1. It's less than a millimeter, for example, the whole sensor. For the other sensors, there is nothing that actually you can buy today that will detect glucose based on sweat or tears. It just doesn't exist. And so I will stop here, and I just showed you that the directed assembly based process can work for a variety of applications, and specifically sensors. And the reason we focus on sensors here, because I think this is the best application right now. It has the most value. If you say I want to do CMOS electronics, first of all, it takes you about 2, 3, 4 years to actually get there. Sensors we can print right now, but also there's a need for sensors. People don't have these sensors that work with sweat, that are cheap, that are ubiquitous, but they have electronics. So we felt that the sensors, especially the medical and bio applications, especially in hospitals, there's a big demand for that. And we thought that using printing would be a very nice way to actually make it available to everyone. And I showed you that the approach is very inexpensive, uses water, it's used very low energy, very low capital investment, and that hopefully would lead to building fabs in the future that will be under 100 million, between 50 to 100 million. So I'll stop here and see if you have any questions.